So, radiative cooling. All objects emit radiation that's black body radiation, and they lose energy via this. It's a very small effect relative to other means of heat transfer, like convection. So it's not usually noticed on Earth, but it's but in certain situations, such as clear nights, you can get frost forming on ambient temperatures that are above freezing, because what happens is that the water cools down and emits all of its energy enough to freeze into the sky, and it cools it enough that it will freeze. Some of the uses that we've already got currently for it are in cooling of spacecraft, because when you're in space, you're in a giant thermos. It's quite easy to just overheat because there's no convection happening. You're in space. So there's some panels, and I'm just going to show you guys on my notes the panels. Switch it over, stream quality, change window. That's the one. Doop-a-doop-a-doop. Right, you can see these. These are radiator panels that are shielded from the sun on the ISS, so they don't pick up heat direct light from the sun when they're in shadow. And what they do is they emit radiation away from the ISS and perform a cooling effect, so they don't cook the astronauts alive. It's pretty cool. It's one of the most prevalently used forms of radiative cooling that we've currently got. So,
I'm sorry. There's some kind of echoey thing in your voice. I don't know.
I will just sort that out for you. It's not a problem, but I'll
Thank
continue
you.
while that happens. Right. So, what's passive daytime radiative cooling? Well, the problems we have with radiative cooling is that it's such a minor cooling effect that other heat transfer methods, such as convection, overpower it most of the time. So because the sun warms it up. So on Earth, it tends to not be that much of that easily, isn't usually noticeable. But it has come into, if we can create panels that allow the right. On Earth, it's difficult. We have an atmosphere, we have a sun, it's always pointing at us. It will and convection is a problem because our atmosphere allows it to warm up objects faster than they can emit the heat and their energy. So and especially during the day, because we have a lot of just power coming out from the sun. So it's to utilize this cooling effect is quite difficult, because what you've got to do is you've got to emit infrared and have it not come back. You've got to emit it into space, and there are only certain frequencies which our atmosphere will actually be transparent to, which is the 7 to 13 nanometer range of infrared, which is quite a narrow range. So and you can, once you get it out of the atmosphere, it's gone. But most of the time, you have the sun. So what people have been trying to do is produce a emitter that performs this radiative cooling on Earth during the day. And for what we have today is a paper which provides a option for using chitosan as a daytime emitter for radiative cooling. What he in this paper, I'm going to switch it over to the paper now, so we don't all stare at the IS test for half an hour. Doop-a-doop-a-doop. Switch it over. The reason why people are wanting to use anything they can that's cheap for radiative cooling is that the current technology involves multi-thousand-pound devices to plate different forms of different silica compounds onto silica wafers to perform any noticeable cooling effect, and reducing that cost is imperative if it becomes a viable technology. So let's move on to the paper. Now you've had a little bit of a background. So I'm going to need, right. Okay, so at the start, what he does, can you see it, by the way? Does it work?
Yeah, can see it.
Cool, right. Let's start. Various applications. Yeah. What the paper covers that a electrophoretically deposited chitosan layer to produce a radiative cooling emitter in hopes of creating a daylight radiative cooling. The gold standard is if you can create an emitter that produces a cooling effect that's lower than the ambient temperature during sunlight. Because of what you need to do is you need to reflect the vast majority of all solar radiation at about 95 minimum to 97% of all that radiation needs to be reflected and not absorbed for the effect to actually have a standard chance in daytime. And for this, and for most of those coatings, you're using silica deposited, or in some senses, some people are looking at using silica particles in plastics and polymers. But this guy looks at using a coating of chitosan on a substrate. I didn't understand. He uses the process. I don't quite understand, which was the electro. Can somebody pronounce it? The electrophoretically deposited. But what he does is he deposits about a 13 nanometer. Sorry, not 13 nanometer. He deposits a thin layer on, and eventually then tests the sample. And what he does is he ends up producing a emitter. I'm going to get to the graph. Wavelength. Where is it? There's the one with all of the. That's the structure. I'll come back to that in a second. Here. He tests samples against with or without chitosan, and he uses a testing rig, which I'll cover in a few minutes. And with chitosan, he makes a notable increase in the efficiency of his emitter, but still doesn't reach the point of a cooling effect below ambient temperature during daylight. It is a remarkable improvement. Reasoning for this, my personal belief is that in his rig, which he produces, he doesn't have a reflector. He is simply measuring the cooling effect of introducing the chitosan to the sample and using it as an emitter. And he goes and he measures the cooling effect and the absorbed radiation. He creates a little polythene little enclosure to try and keep the convection losses due to convection down, and he creates little polythene polystyrene windows to it's one of the plastics that transmits infrared quite reliably and is also quite clear to standard, solar radiation. And he sees a notable improvement. Now, I've spoken for a long time. Could I have any questions? Or things you don't quite understand?
Can I ask? What is the purpose of this cooling? Does it have a specific purpose, or is it universal?
The purpose of this cooling, it's a bit contested at the moment what the purposes are. Currently, Stanford and MIT are trying to create this cooling effect in an attempt to aid air conditioning of climates, like habitable climates, more efficient by taking the load off absorbed heat. If we can emit some of our heat without having to use refrigeration.
May I add something to the question?
Go ahead.
It's basically you have every time, let's say a satellite, even a microsatellite that we send out there, every time it's gonna use one of its device, its component, when you use energy, electricity, it's gonna generate heat. And if you don't have a way of dissipating that heat, it's not like in complete vacuum, you don't have anything to dissipate heat other than light emission. I'm currently trying to find the relation between the Faradic effect and the Planck's constant and the Planck law, but their two are like related. Like yeah, that's it.
Yeah.
But isn't this like for the large scale cheap things?
Yes. Exactly.
So this paper, or the technology from this paper, isn't specifically for satellites. It's for land use.
Yes, it's for it's reducing the cost of a daylight emitter down from a couple 100,000 per square meter to pennies.
Okay.
Because we can provide cooling via refrigeration with reasonable efficiencies by creating power, capturing it, using it to power a refrigeration cycle, and then using that. This is a truly passive means, but it's not economically viable to coat your house or coat your area in something that is more expensive than gold.
So a way to think about this is, if you've ever built a computer, you have like your heat sink. You usually put a heat sink in, and then you also have like a fan. And if you get really crazy, you start doing like liquid cooling and stuff like that.
Yes.
This is about making really, really cheap heat sinks, like things that dissipate heat passively, because that's what it is. A heat sink is an inert piece of material.
Yes.
Yeah.
This is exactly that. I am personally looking at it for trying to provide a cheap heat sink for using low quality temperate geothermal energy, because the difference between the temperature of the ground and the ambient air is so little that you can't produce any work with it. But if you can reduce that temperature down, you can start working with that temperature gradient, which is where I come to this some of the research I've done, because this paper on the Kitesurn was a byproduct of finding out about this material. And I'm going to have to switch to a webcam because I've got things to show you guys, because yay, we watched paint dry. It was fun. Everyone, right. Let's show the stream. Stop streaming. Right. You see this on these two materials? One's a bit wrinkly. Can everyone view these?
I can
I can
see
see it, yeah.
white squares.
Oh, now I
Yeah,
can.
yeah.
Yes.
Right. These are something I've been working on by myself and also in conjunction with Ollie, because I need somebody to tell me that the plastic is the correct plastic. I didn't include this here because I'm still working on this and I don't truly understand it, but this is a formation of creating this little goop, which is an acetone water mix of a polymer. In this case, it's PVD. Hang on, Ollie, do you remember what it's called? It's PDVP. It's a fluorinated
Polyvinyl hexaiode, something like that.
Yes. And the actual material itself isn't actually that necessary, because what the big part of the paper that we found was the cooling effect that this panel can produce when you evaporate it after painting it. You know, you dissolve it in acetone water and you paint it onto it. It creates a is it vertically or horizontally lined?
Hierarchically aligned pores.
aligned pores that produce a ridiculous reflective material. This is just a matte plastic, but when you put it on a sample, it reflects light like nobody else's business. And he showed it works with not just this material. I was going to have a look and see if chitosan can also be used, because he showed it used with cellulose and other, I forgot the other plastics, I can bring them up. But he went rummaging in his bins and found other things he can do. And some of them are more effective than this, but this fluorocarbon plastic was the most effective. And yeah, you basically roll it on. That's basically it.
It is literally a paint. You could put it in a spray can, spray it on everything, paintbrushes, whatever you can use to get it on a surface, and it will paint that surface.
I don't know if it was like something with the camera at some point, but I was with Ollie and we were actually watching Baconator doing his watching paint dry experiment on this PV thing. And he hit a moment of reflection when he was basically having it right on top of a cardboard, like a brown cardboard piece. And I don't know if it was like the camera bugging or something, but it basically almost got in like brown as the cardboard. Like it had like a photo reflective effect that basically it got invisible to the camera. It was insane, and I think it actually is due to the angle and how to.
I'm going to just post the paper that I'm also referring to here, just in the chat if I'm able to do so. Should be, it's under 4 gig. Because this is a one spin. Should have upload the thing. So there it is. Upload, right.
And I wish we had that moment recorded, because I'm pretty sure I was not the only one seeing it. Like it blended in the cardboard, like from being completely reflective, it got brown. Yeah, you saw it too, Baconator, right?
Yeah, I had it. I've got it on time lapse, but I didn't at the time. But it was one of those times when it was just like, hang on, what the fuck is this? But yeah, his paper on the chitosan, it shows good promise with using the coating the chitosan. But but the fact is, he doesn't include a mirror to block the broad spectrum of light, which for most for this effect use either a silver mirror or a aluminium mirror, both under vacuum. So they just have a big vacuum chamber with the emitter in it, and they have the mirror, which increases cost dramatically, which is where this fancy metamaterial, like goddamn, it's goddamn magic. Can make is the camera on? I don't know if I did or not. But yeah, want to try making this out of the chitosan, because this is a fluorocarbon. It's not expensive, but it's not exactly cheap. And if we can, and showing just the characteristics of the chitosan with the without any ability to block out the majority of the sun beforehand, be good. Yeah, I've spoken enough right now. I'd like to hear from you.
Do you have the protocols, the recipes for the paints that you've made so far?
Yes, I do.
Will you write those up and throw them in a folder, please?
Oh, I will definitely do that. That's why I've been doing it recently, because they're all written like the, here, in books. But yeah, it is as simple a part as, let me just flick through. Yeah, it is just a simple weight, a ratio by weight of acetone, the polymer, and water. It's always you say the story, because it was it best comes from your mouth.
Which one?
When we found out there's a one-step method.
We were just in the chat, and he commented on it offhand, and then shared the paper. And you literally go through it, and there is a single paragraph where the beginning of the paragraph is meaningless, the end is meaningless, and there's one sentence that describes the entire process of creation. And it is measure out a ratio of 1 to 7 to 1, dissolve them together, and then put it on surface. That's the whole protocol.
Yeah. I have found that aluminium does not make a good substrate. It doesn't like sticking to it. Made finding out whether it was actually having an effect hard, because it wasn't gaining much thermal conductivity to the thermocouple and the substrate at all. It just sort of peels off. Haven't got currently any other substrates apart from aluminium. It's just I just rummaged in the bins, honestly. We've got a big scrap bin. I'll find something a little bit better. But yeah, he worked with copper. That's something I should also try to replicate. But yeah, trying to create this magic wrinkly goo. Yeah. Feedback, questions, like uses. I'm all ears. Huh?
Someone must have questions, right?
Well, I had a small question.
Go ahead.
Maybe it's just because I haven't completely read through the paper. Was there any mention of how the chitosan was linked, or is it just an additive?
I don't know. That's purely for my lack of knowledge in chitosan. I don't know. Because I don't understand how it was actually attached to the substrate. That's something I
Okay.
understand. It's from what I gathered, from my knowledge, it's attached to the substrate by some means, and it's a layer, and it was placed in thermal isolation, just some cut out foam. It was polystyrene foam with some polyethylene film. Otherwise, it was film and cling film, and it was isolated from the foam with little wooden needles. So it was made with toothpicks and foam, which is fantastic. My first experiment was a coffee cup, because we found out that the ground was so warm relative to the ambient air that we needed something to isolate it with. You show pictures of that. in the chat.
Yeah, and to clarify for anyone who didn't understand that the attachment method is like a really fancy word for we ran a charge through it. They basically put it in solution and ran an electric charge through it. And so in the same way in basic chemistry, you learn how anodes and cathodes work and how over time the ions will build up and you'll get like a molecular buildup on one of your poles. This is the same type of thing, except they were doing it on purpose to make a film.
Oh wow.
Yeah.
Yeah, because this part of my script is really ad hoc now, because 2 days ago somebody made the thing and made it better, and I had somebody from the workshop come and was like, here, isn't this what you're doing? And I go, yes. I have no idea what they're doing, but they did show how they literally just took a sponge and, you know, painted it on, like with a roller even. It's something I don't quite understand and need more research on, because yeah. Yeah, because it's promising the improvements of using chitosan in this, but isolating it from the thermal radiation is the hard part, because you know, water is a really good emitter, but it's also only really works during the night, and nobody's thought, and let's hook thermocouples up to lakes, as you know, as the next thing since sliced bread. Sorry, I was just rambling then for a second. Sorry, this is a little unprepared because I didn't realize due to the timing that you guys aren't on. You guys are on not on daylight savings where we are. So yeah. Right. Is that it really? Any other questions? Any other problems? Any like
I have
use
a question.
case? Sorry. Yes.
So one, when do you think you can release your notes on like what you figured out about how to do this?
When I've typed them up.
Great.
I have them. I have them physically here. They're in a notebook. I haven't had a chance to scan them in yet, honestly, because we only did the experiment on last Friday. Yeah, because it was.
Cool.
Yeah, it was Friday. Was it Friday or Saturday? It was very rushed because we've had the hours cut at this place because of COVID. So we did the whole thing in less than 12 hours, and it was very stressy.
Okay, and the other question was, how much was the total cost on this to do it?
The cost of the one I did, which was the plastic, was free because I got a free sample because Sai sent me a free sample. P.S. Thanks, Sai, you're awesome. Because it was otherwise Sigma Aldrich were going to charge me £44 for about 120 grams of the stuff. It's not a very expensive plastic, but it's really expensive in small quantities. And the other two ingredients was a tenner for deionized water and that was 5 liters of water, and it was a tenner for a liter of acetone, and I used 12 grams. So it was theoretically really, really cheap to do a small sample. Did you catch all that?
All right, cool. Thank you.
No problem. Anybody else? So didn't freak out. That's good.
So you dissolved the chitosan in acetone?
No, I dissolved the PVASH.
Okay.
Yeah.
A plastic.
Because because I wanted to recreate this because I have it on hand and I don't have Kitezen on hand. I had 2 days. So I'm going to try doing the Kitezen when I have access to some Kitezen, and try and get this working first, because change one variable, then other variables. Once I got this working, because it's proven.
I think I found something on Kitezen, and it's a jump. Yeah, you may want to look at this whenever.
Yeah. So, is that in the voice link?
Yeah, voice and digitize. Yeah.
Yes. Because how this material operates does two things in one. One being the emitter, because it selectively emits at the